So we're going to continue with practicing examples of curve sketching. We're going to continue to follow those 6 or 7 main points in order. So today's example that we're going to work on is y equals x squared e to the minus x. This is a little bit of a polynomial mixed with an exponential function. The nice thing about this example is likely most students won't know what this example looks like, so it's nice because you can use the information to help you sketch this graph. So first things first, we want to do domain. Now when we're doing domain, we're looking for denominators, we're looking for square roots and negative numbers. If I rewrite this function with the e to the x on the bottom, we know that e to the x is an exponential function, kind of like the growth function, where the equation y equals 0 is a horizontal asymptote. So the function will never cross the x-axis, which is nice because that makes our domain the set of x such that x can be any real number. Okay, remember we're going to summarize our key information by highlighting it. Intercepts. So x-intercepts, y-intercepts, we look at the factors. So you can either look at the function with the e to the x on the numerator or the e to the x on the denominator. We ask ourselves, what makes x squared equal to 0? Well, we know that clearly that's x equals 0. Where does e to the minus x equal 0? Well, it never does. So my only x-intercept would be 0, 0, and that would also include my y-intercept, because if 0, 0 is an x-intercept, there can only be one y-intercept. Let's work through to the symmetry. When I want to calculate the symmetry, I'm going to compute f of negative x and compare it to the original function. So negative x squared e to the negative x, which is x squared e to the x. Now the thing is that when you look at the exponent on the e term, this is a positive x. There's no way you can kind of revert back to that negative sign, so there's no symmetry here. It's going to be a clear-cut odd or even if it's going to be even or odd, and if it's not, it's just clearly no symmetry. So there's no way to gain back my original function. Asymptotes. Now, usually when we're doing asymptotes, we would look at the denominator for the vertical asymptotes. So if I look at my function as y equals x squared over e to the x, I have a denominator, but that denominator will never equal 0. So there are no vertical asymptotes. My horizontal asymptote, I would take the limit as x goes to infinity of x squared over e to the x. Now we've never done this example in class, but there is a rule called L'Hopital's rule, and I'll kind of briefly explain it here. If you take the limit as x approaches infinity of the numerator, this gives us infinity. And if I take the limit as x approaches infinity of the denominator, e to the large number is a large number. Since this is the indeterminate form infinity over infinity, L'Hopital's rule can apply. And what L'Hopital's rule says is if you have an infinity over infinity or 0 over 0, and some other conditions, which we'll talk about when we actually do this lesson, there's like continuity and differentiability and that kind of stuff. It means when you have either of these indeterminate forms, you take the derivative of the top by itself. So the derivative of 2 or x squared is 2x. The derivative of the bottom is e to the x. And you try to evaluate the limit again. So if I do limit as x approaches infinity, I get limit as x approaches infinity of 2x, I get infinity. Limit as x approaches infinity of e to the x is e to the x, e to the infinity, which is infinity. Again, it falls under the infinity over infinity type. So I would do L'Hopital's rule again. Take the derivative of the top, take the derivative of the bottom. Now here you're not doing quotient rule or chain rule or product rule unless it shows up, but we're doing the derivative of the top, the derivative of the bottom separately. And now I'm going to try to evaluate the limit. This would be 2 over e to the infinity, which is 2 over a large number, which will tend to 0. So that means, therefore, y equals 0 is a horizontal asymptote. Now we also want to do the limit as x approaches minus infinity. So limit as x approaches minus infinity of my function. Now I'm going to leave it in this form. So this would be negative infinity squared, which is a large number, e to the negative of negative infinity, which would be e to the positive infinity, which would be large number times large number, which is large number. So here I get y equals 0 as a horizontal asymptote, no vertical. So again, we're going to start doing a rough sketch of our graph as we move along. This time I'm going to do the sketch up here and do the derivative information below here, and we'll come back to the graph. So as x approaches minus infinity, the graph is going up to positive infinity. And as x approaches plus infinity, my graph has a horizontal asymptote at y equals 0. So I'm going to only put that at the end. We have an x-intercept at 0, 0. So this is why it's important you only put the dotted line at the end, because again, here's a point that crosses the x-axis, but y equals 0 is still allowed to be a horizontal asymptote. And other than that, we don't really know much other than that. We just kind of know that that's going to be the behavior. Let's continue on and do the derivative. So let's do all our first derivative stuff. So let's go ahead. Here's my original function, x squared e to the minus x. I'm going to go ahead and do product rule. So the derivative of the first times the second plus leave the first the same. The derivative of the second is you leave the exponential the same. Derivative of the exponent is -1. Now you'll notice in both of these terms, there's an x and an x squared. So x is in common. And e to the minus x and e to the minus x are in common. So I'm going to go ahead and factor those out. So I'm left with 2 minus, because there's a minus sign, and then there's an extra x that hasn't been taken care of. And that is going to be my simplified derivative. So we want to ask ourselves, where does the derivative equal 0? So you're going to get x equals 0, 2 minus x equals 0, so x equals 2, and you could have e to the minus x equals 0, but this is not possible. So I get 2 critical points, and there's no points where the derivative is undefined. I have 2 critical points, one at 0, one at 2. I'm going to test the signs in my derivative, and then I want to say something about the original function. So when we do this, you want to remember that the e to the x graph is always above the x-axis, which means the y values are always positive. So my e to the x term here is always going to be a positive value. So I'm going to kind of ignore that in my sign analysis. So when I take a number like -1, the term here is going to be negative. And then 2 minus a -1 is a positive. So a negative times a positive is a negative number. When I take a number like +1, I get a positive. And then 2 minus 1 is 1, which is also a positive. So I get a positive result there. And when I sub in a number greater than 2, this is positive. But that second term is negative. So I get an overall negative result. What does this tell me about the original function? We're decreasing, increasing, decreasing. So let's summarize our intervals of increase and decrease. F of x is increasing on 0 to 2 because f prime of x is greater than 0. F of x is decreasing on -infinity to 0, union 2 to infinity, because f prime of x is less than 0. Okay, so let's come back and highlight that. That's part of my solution, because I would ask you for all this information. Now we're looking for sign changes. So the sign changes from negative to positive, so it goes down and then up. So f of x has a local minimum at 0, 0. We know that that's the y coordinate because that was our x and y intercept, because f prime of x changes from negative to positive, and then we know that f of x has a local maximum at 2 comma, I'm going to come back and find that y coordinate, because f prime of x changes from positive to negative. So now let's come back and find this y coordinate. So this would be y is equal to x squared e to the minus x. So y at x equals 2 would be 4e to the minus 2. So this would be 4e to the minus 2. Now again, if you needed to approximate that, e is approximately 2.71. So let's say I take 3, I square it, I get 9, and 9 times 4. Oh, never mind. E to the negative 2 would be 1 over approximately 9. And so you get a 4 over 9, which is kind of less than 1. So again, without a calculator, it's okay if you want to use a calculator to just kind of get the approximate decimal value of that so you can graph it a little bit accurately. Okay, so let's take this information and plot it on my graph. So 0, 0 has a local min, and at x equals 2, there's a local max. So let's look at my graph here. So I know that the graph has to kind of come down. This 0, 0 is a local min, so I know it has to be doing something like that. Now at x equals 2, let's say here is x equals 2. There has to be a local max there, and then it has to go down towards my asymptote. So before I kind of conclude that this is my graph, let's check the increasing, decreasing part. So my signs on the first derivative were negative, positive, negative. So you can see slope is negative, slope is positive, slope is negative. So that matches up. And now we're going to do the second derivative to check the smiles and the frowns, or the concavity of the function. So let's go ahead. We're going to work out the second derivative. So my first derivative simplified was x e to the minus x, 2 minus x. Now when I do the second derivative, what I'm going to do is I'm just going to distribute this out to make my life a little bit easier. I'm going to get 2x e to the minus x minus x squared e to the minus x, and I'm going to treat it as product rule. So there's one function, and there's one function, and then this will be another, and this will be another, and I'll do 2 sets of product rule. So the second derivative is derivative of the first times the second, plus I leave the first the same. Derivative of e to the minus x is e to the minus x, and then chain rule says multiply the derivative of the exponent, minus, now I'm going to leave the minus on the outside of everything, derivative of the first times the second, plus leave the first the same, derivative of e to the minus x will be negative e to the negative x, and then I'm going to distribute that negative in. So what we're going to get is we're going to get 2e to the minus x. This term minus 2x e to the minus x, and this term with the negative sign will give me a negative 4e to the minus x, 4x e to the minus x, and then the last term would be negative x squared e to the minus x, and that negative and negative would make this a positive. Now we're going to clean this up a little bit. So all of them have an e to the minus x. So I'm going to factor that out. And then I'm going to get 2 minus 4x plus x squared, like a quadratic. I'm going to just do it as e to the minus x and just switch my quadratic around. And there is my second derivative simplified. We need to find the critical point. So e to the minus x equals 0, not possible. X squared minus 4x plus 2 equals 0. I need to determine, is this quadratic going to factor or not? I'm going to do the discriminant, b squared minus 4ac. So 16 minus 8, which is 8. So I get a positive discriminant, which means I am going to get solutions. X is equal to 4 plus or minus root 8 over 2 times a, which is 2. And clean that up. I divide each term by a 2. So 2 plus or minus the square root of 8 is 4 times 2. So this would simplify to 2 root 2. And I divide, hold on, I'm going to kind of just do one more cleanup step here. I'm going to leave that at 4 over 2. And then I'm going to divide each term by 2. So I get 2 plus or minus root 2. So those are my critical points. I'm going to throw them on a number line. Now be aware, in the future you would not necessarily have a calculator to do this. So 2 minus a root 2 is going to be a smaller number than 2 plus a root 2. Take a number in between, so 0, sub it into my function. Remember, e to the minus x is always positive. So the sign is going to be determined by the quadratic. When I sub in 0, I get 0, 0, and a 2. So that's positive for my second derivative. Now 2 plus root 2 is approximately 1 point something. So when I choose my number here, I'm going to choose it like 5. 5 squared is 25. 25 minus 20 is 5. 5 plus 2 is 7. So that's going to be also a positive value. Now, you can see I've made a careless mistake here. I can't choose 0 for this because this is 2 plus a little bit. So 2 square root of 2 is approximately 1.4. So this is 2 plus 1.4, which is 3.4. This is 2 minus 1.4, which is approximately 0.6. So we need to choose a value. The positive for the 0 would be here. My apologies. And then when we choose a value like 1 for that one and sub it in, I get a negative value because 1 squared minus 4 plus 2 would be negative. What does this say about my original function? Concave up, concave down, concave up. So let's write our sentences. Y double prime is concave up on, and again, you can use y double prime or f double prime at x is, whoops, we don't want to talk about the second derivative, we want to talk about the original function because we're talking about f or y, is concave up on the interval negative infinity to 2 minus root 2 union 2 plus root 2 to infinity because our second derivative was positive. F of x is concave down on the interval between the two of them because the second derivative is negative. And now we want to talk about inflection points. So we're talking about where does the second derivative switch signs. So there's a switch and there's a switch. So plus to minus, minus to plus. F of x has inflection points at 2 minus root 2 comma some y coordinate, 2 plus root 2 comma some y coordinate. Now, to be honest, I don't really care about where these y coordinates are. It's more important to know sort of where the x's are. So this is approximately 0.6 and this one is approximately 3.4. So I'm just going to locate my maxes and mins, or sorry, my inflection points on the graph using the approximate decimal values. But again, if you wanted to kind of know where that sits, you would need to sub that into your original function. And you could leave your answer like this for me too. Sometimes it's nice to show me the y-coordinate, but the other thing you could do is just go f of 2 minus root 2, f of 2 plus root 2. You would just sub it back into the original. So let's check. We need to have a smile. So let's put the inflection points in. 2 minus root 2 is approximately 0.6. So I'm going to come in green. There's going to be an IP. I'm going to call it inflection point. And then at 3.2, somewhere over here, there's another inflection point where it's switching concavity. So up until this first inflection point, the graph is concave up. It's smiling, which is correct. Then it's frowning, and then beyond that point, it's smiling, which it looks like it's correct. Key points to label on your graph are the max and mins. This is 2, f of 2. You can label that y-coordinate if you wish. This point was 2 plus root 2, comma, f of 2 plus root 2. Now you could work it out if I asked, but I don't really care much for it right now. This one was 2 minus root 2, f of 2 minus root 2. And then here we have a local min at 0, 0. And we've already labeled our horizontal asymptote at y equals 0. And there's the function sketched